YouTube. This is my last video on graphing rational functions, but one in which I'm going to point out a particular instance in which we have no horizontal asymptote, but what we have is specifically a slant asymptote. Okay, so you can have non-slant asymptotes, you can have parabolic asymptotes, you have cubic asymptotes, weird asymptotes, but I'm only going to give an example of what we call a slant asymptote. So let's just go ahead and get started with this one. As a matter of fact, we'll start with how we usually do, which is simplify the top and bottom. That means we're going to factor the top and the bottom. And I notice at the top, it doesn't factor, and the basement, it doesn't factor. So I guess we're done simplifying this. We can go ahead and dip right into what we've been doing, which is start by finding the y-intercept. We're going to find the x and y-intercepts, a y-intercept and x-intercept respectively. So the y-intercept means we plug in 0 for x. We say, well, what do we get for y? And in this case, you'll notice that if you plug in 0, as a matter of fact, you get 1 over 0. So this is undefined. So this means that will it ever hit the y-axis? As a matter of fact, it never does hit the y-axis. And clearly there's a reason why. It's because if I try to plug in 0, it's undefined. We're going to determine that it does actually have a vertical asymptote there. But anyways, let's take a look at the x-intercept. The x-intercept says, well, I'm going to take the whole expression, I'm going to set y equal to 0, the whole thing equal to 0. And the only time that this ever occurs is if the top of the expression is equal to 0. So what we need to do is, this is kind of a complex one, we're going to set the whole top equal to 0, and we're going to solve for any real values that would cause this to happen. So if I were to do, solve for x, we say 3x squared equals -1. So x squared is -1/3. And basically, I'm going to stop here in just a second, because when I take a root of this, I notice that root -1/3, not that I need to keep simplifying here, but I get this, I get I, plus or minus I times the square root of 1 over the square root of 3, which is plus or minus, basically root 3 over 3 when you rationalize it, I. So the point I'm trying to drive at here is this: there are no real numbers which this is going to hit the x-axis, so we say none. It has no x-intercepts. Okay, so hey, I know something about my graph. It never hits the y-axis, never hits the x-axis. Cool. Moving on, we say, all right, vertical asymptotes. Well, here's one big reason why it never hit the y-axis is because where would this be undefined? If I set the basement equal to 0, I said, well, it's 0. So we say I have a vertical asymptote at x equals 0. We need to go throw this on the graph here. We say x equals 0. I'm trying to get it so you can see it here. I'm trying to draw it off to the left a little bit, and I'm not doing a very good job, but we say x equals 0 is a vertical asymptote of this, and then we say let's go find the horizontal asymptote. Now, up until now, what I can say is this: we've mentioned that you either have a horizontal asymptote or you don't, and what we're doing to determine this is we're comparing the degree of the top to the degree of the bottom. I notice that the degree on the top is heavier than the degree on the bottom, so what we can say is that it has no horizontal asymptote. Now, the thing that is important to mention here is this: if it is top heavy, we need to look for what we call, at least with my students, I'm going to give you what we call a slant asymptote to look for. But basically we say, well, where would that be? And what the heck is a slant asymptote? And so in terms of a slant asymptote, by definition, it's just an oblique line. Maybe it runs like diagonally, but it is an asymptote that our graph will approach as our x values go way out on the left or way out on the right. And the way we determine is this: it is the quotient of the numerator and the denominator. Okay, and when I say quotient, I mean not the remainder, but essentially when I say it's the quotient, let's go ahead and do this. We are either going to use long division or synthetic division. This is entirely up to us. But we're going to use one of those to find the quotient between the top and the bottom. And in this case, I noticed that in the basement here, this is a linear divisor. Actually, I'll re-scribble this down here. We say 3x squared plus 1, and we're dividing this by really x minus 0. So I can clearly see that this is a linear divisor. But what we want to do is let's use synthetic division, actually. Synthetic division will drop in our array here, and I notice that I have 3 x's being squared, I have no x's to the first power, and I have one constant, so x to the 0. And then out here we say, well, what would I put out here? I say, well, let's throw in a 0, okay? But here's what I want to point out. When we drop down this 3, I get 0 times 3 is 0. 0 plus 0 is 0. 0 times 0 is 0. And then I get this 1 right here. But recall that this thing is what we call the remainder. And that everything else over here, this right here, this is our quotient. Okay, so this is the important thing. What I can tell you is this: the slant asymptote is always located, and I'll write the quotient back in here. As a matter of fact, this is y equals 0 constants and 3 x's. We get this, y equals 3x plus 0. This right here, this quotient, is actually the equation of our slant asymptote. And notice I said not the remainder. I don't care what the remainder was. I was after this part right here. So let's point one thing out. We took a second degree divided by a first degree. So I've got second degree divided by a first degree, knock out a degree, got one left. But basically, the thing that's going to be left over here was guaranteed to be a first degree thing. And I only usually ever use slant asymptotes that are lines, okay? So you get left with a first degree quotient. But again, that is the equation of our slant asymptote. So what we're going to do is we're going to graph this equation. We say, all right, well, my y-intercept is 0. I mean, it's not actually there. We're just graphing this as an imaginary thing. And my slope is 3, so I go up 3, right 1, up 3, right 1, up 3, right 1. I could go down 3, back 1, down 3, back 1, down 3, back 1. Essentially, this thing right here, go ahead and drop in to the best of your ability. You should use a straight edge. I do not have one, but we're going to drop in this line right here, and we're going to label this y equals 3x. In other words, I got 3x because I just took the quotient of the top to the bottom. I didn't care about the remainder, but that quotient is always the equation of our slant asymptote. So now, when we go graph this, we're going to do the same thing we've been doing in the other videos, which is basically, let's throw in some extra x values. You know, if we table this out, we want to table this. We say x, y. I'm going to pick two x values to the right and to the left of every, say, undefined spot or 0. So I had no zeros, but I do know this. I say -2 and -1 are two x values to the left of x equals 0, which was undefined, and then 1 and 2 are also to the right of this undefined spot. So when we plug these in, I do have this expression. We say 3 times my input squared plus 1 over my input. And so when we plug in 1, let's go ahead and take out, look at what we get here. We get 3 times 1 squared, so 3 times 1 plus 1 is 4, and this is over 1. So basically, when we plugged in 1, we got 4, okay? So our output is 4. When we plug in 2, we say, all right, well, in this instance, I get 3 times 2 squared. In other words, 3 times 4 plus 1, so I'm going to get 13. And this is going to be over 2, and 2 goes in that 6.5 times. So 13 halves is how you're going to see me list it, 13 halves, but you can make that a decimal if you want, a 6.5. Now when we plug in -1, this is interesting. -1, I get -1 in the basement, obviously, but on the top, when you square this -1, it becomes positive again. And so you see that I get 3 times 1 plus 1 is 4. So this time I don't get 4 over 1, I get 4 over -1, which essentially means this. I'm going to get -4. So the opposite of what I got here. And we're going to see here when I plug in a -2, the same thing's going to happen here. I'm going to get -2 in the basement, but on the top I'm going to get 3 times 4 basically plus 1. So I get -13 halves in this instance. So when we graph this, let's go ahead and take a look at what this would look like. We say at 1, I'm at a height of 4. So right 1, 1, 2, 3, 4. We're going to draw on this dot right here. So 1, 4 is on our graph. And we say also 2, 6.5. So over 2, 1, 2, 3, 4, 5, 6.5, up 6.5. Okay. So now I have kind of the right side of my graph here. The left side of my graph, we said at -1, I'm down 1, 2, 3, 4. And at -2, I'm down 2.5 more. I'm down at 6.5. So really close to this asymptote. But knowing what we know about asymptotes, we say, well, it doesn't have a horizontal asymptote. But horizontal, recall, I said, as x gets very large, as we go way far out on the right or way far out on the left, that horizontal asymptote was what our graph was approaching. Well, in this case, we have this slant asymptote. And as we go way far out on the right, this is what our y values are going to approach. They're actually going to diverge to infinity. And then we know that as we come into this undefined spot, or x equals 0 from the right, that our y values would increase without bounds. So we get this graph right here that looks like this. And then on the left side, we say, well, this was decreasing without bound and must be coming up. And then it approaches as x gets very small. You know, imagine we keep going way out on the left here. It's going to keep approaching this slant asymptote. But this would be a graph that would contain a slant asymptote, and a really good one to keep in your notes.